So hello everyone, I'm Hong Yi Li. So this presentation is about how to teach language model to listen and speak. So in this talk, we are going to focus on spoken language model. For spoken language model, I mean a language model which can take speech as input and response with speech signals. But different from typical text language model, this model can not only understand the content in the speech signal, but also other information like speaker characteristic, emotion, or even environmental sounds. So this is the outline of today's talk. We will start from a text language model, and I will show you how we fine-tune a text language model that can take speech as input and text as output. And in the second part, I will talk about how to fine-tune a text language model so it can take both speech as input and output. And in the last part, I will talk about a speech reasoning model. It's a speech-to-speech model, but it also do reasoning simultaneously. So let's start from the part one. So how to make a text language model listen? And I believe you have seen similar paradigm in many papers in Interspeech. The basic idea is you already have a text language model which can take text instruction as input and respond properly. What you have to do is teach the model to understand speech signals. And today, you will not directly give your text language models those speech signals because they are too sophisticated. Usually, you have a speech encoder transform sophisticated signals into representations or tokens. Then the text language model will take the representations or tokens as input. But those text language models are originally trained to understand text token, so they cannot directly understand speech representation. So you need to fine-tune the adapters in the text language model. You need to insert adapters into the text language model and fine-tune the parameters in the adapters. And to fine-tune these adapters, you need some training data. A typical paradigm today is you collect some text related to speech, and you train the adapter with this speech-related text. For example, you give a text language model an utterance, and the text instruction is please transcribe the utterance. Then you fine-tune the adapter so the text language model can output the transcription. And you give a text instruction, please identify the emotion in the audio, and you fine-tune the adapter so the model can output the emotion label. So this is lots of people try to teach text language model to listen today. This is a very typical paradigm. And we start to look in this direction 2 years before 2023, because it is a very early stage. So at that time, there's no benchmark to evaluate spoken language model. So to evaluate spoken language model, to make the research advance, we need to create a benchmark ourselves. So this is the motivation to create dynamic super. This is initiated by Xinqi, and my group is mainly done by one of my students, Jian Yong, and David joined the second phase of this effort. So in dynamic super, for each testing example, we have a text instruction and an utterance and the ground truth. In the first phase, we collect more than 55 tests, and now the second phase is online. So if you are working on spoken language model, we'll come to use the second version of the dynamic super. It includes 180 tests, and it's very sophisticated. So we not only include speech-related tests, but also audio and music-related tests. And you can find that the taxonomy is so sophisticated. So for speech, we have main category. For main category, we have subcategory. For subcategory, we have sub-subcategory, and we have sub-subcategory. So it's very sophisticated. Okay, so now we already have the benchmark. By the way, today there are so many benchmarks. So my student even write an overview paper for the benchmark of speech language model. I have to highlight that this is not an overview paper for speech language model, but overview paper only for the benchmark for speech language models. Okay, now we already have the benchmark, so we can evaluate the model. Now we can start to train the model. So our first trial is we have some in-house training data, include 23 different tests. So we use this 23 speech-related text to train the adapter in a text language model, and we evaluate on dynamic super. In our setting, some of the tasks in dynamic super do not exist in the training dataset, so they are unseen tasks. And there are some tasks has been seen before, but their data is different. So we do not have overlap between the training and testing dataset. The initial result seems to be encouraged. So here we show the result, average result on different category. Here we show the accuracy. So the larger, the better. The blue bar is the result of random. So worse than random means your model is really very poor. The blue bar is the result of the cascade of an ASR system and a text language model. And you can find that this kind of model achieve poor performance on some category. For example, on speaker-related tasks. The model achieves very poor performance, and this is reasonable because if you only transcribe speech signal into text, then there's no speaker information, so of course the text language model cannot get the correct answer. Then our model is the yellow one, is a cascade of an whisper encoder and a llama model. And we get the yellow bars, and it's better than the cascade model in many different cases. This is our initial result. At the very beginning, we think the result is very encouraging. However, after we take a closer look to the result, we found that the model probably kind of fitting to the training test it has seen before. If we compare the performance of the seen test and unseen test, we found that the model do not work well on the unseen test. It looks like the model do not develop emergent capability from the training test. It cannot generalize to the test it has never seen before. Then, what's our next step? One possible solution is to collect more and more tasks. Probably if we have sufficient number of tasks in the end, the model will have the emergent capability and it can generalize to the new task. So this is one potential direction. But we consider another direction. This direction we call descriptive speech and text alignment, DESTA for short. This effort is mainly led by my PhD student Ke Han and a group of NVIDIA researchers. So our first finding in a series of work called DESTA is actually you don't really need to collect lots of different tasks to train a text language model to understand speech. Actually, train the model with one task is sufficient to generalize to other tasks. We found that if we train the adapter for audio captioning, then the model has potential to generalize to other tasks. So for audio captioning, I mean you ask the model to describe the audio, then the model will provide all aspects of the description for the input audio, including the gender information, transcription, the emotion of the speaker, or all the other characteristics included in the audio. We found that trained on this task, the model has the potential to generalize to other tasks. You may have questions here. If we only teach the model to do audio captioning, doesn't that mean the model can only do audio captioning? How can it generalize to other tasks? You are correct. If we directly ask the model a question after train on the audio captioning, it cannot directly respond correctly. Here is an example. If we train the model to do audio captioning, then we ask the model what is the gender of the speaker. Then the model will not directly respond to your question. It just do audio captioning. It just describe the input. Because this is the only thing you teach the spoken language model to do. However, we found that in the literature, there is a tip to make the model less overfit to the training task. This tip is from another spoken language models paper called Silman. They found that if you multiply a constant on top of the adapter and make the adapter has less influence to the whole model, then your model has less overfitting to the training data it has seen before. Here we use LoRa, and we multiply a coefficient called alpha on top of the output of LoRa and make the LoRa have less influence. And we found that if we set alpha to 0.75, then the model starts to answer the question. When you ask the model what's the gender of the speaker, the model say the speaker gender is identified as female. 0.5, the model also answer the question. Of course, you cannot make alpha too small. If you set your alpha equal to 0, then it's not a spoken language model anymore. Then the model is become a text language model, cannot really answer the question related to the speech order. So this is the first finding. But later on in the second paper of DESTA, we call it DESTA 2, we found that it is not necessary to use the trick. If you create the audio caption, create your learning target properly, then the trick to modify the output of LoRa is not necessary. Here, create properly means the caption has to be generated by the text language model you use as the backbone. So here, when train a spoken language model, we start from a text language model. If you use the same text language model to create the audio caption, then you don't really have to worry about the overfitting issue. So this is how we train the model in DESTA 2. So given the training authors, we have some labels. We have its gender, emotion, or accent, or transcription. We have these attribute labels, and we provide the attribute label to a text language model. The text language model can only take text as input, so it can take attribute labels as input, and we ask the model question, what can you hear? Then the model will generate the output. This output looks like the audio captioning. Then we use the output of the text language model as the learning target. When we train our spoken language model, we provide the same instruction, what can you hear? And the model learns to generate the same output as the text language model. So this is the training process of DESTA 2. I am going to show you after a few slides that using the same model for generate the caption, and the backbone of a spoken language model is very critical. So during the training time in DESTA 2, we only teach the model what can you hear. This is the only instruction we use to train the adapter. However, during the inference time, you can ask all types of questions. You can use all types of instructions, and usually there is a potential the model can give you the correct answer. And there are other related work use similar strategy. BLSP is earlier than DESTA 2, and DIVA is a concurrent work as DESTA 2. And I would like to show you this approach is very powerful. Recently, we released DESTA 2.5 audio, so you can get the model from the link I put on the slides. And we start from Llama 3.18 billion parameter. We use 50 public available dataset, including more than 5,000 hours of speech, 1,000 hours of environmental sound, and 500 hours of music. I also list the type of labels we use on this slide. So we use the same approach as in DESTA 2 to train the model. So DESTA 2.5 have much more data. And this is the result we can obtain. We first evaluate the model on a dynamic super phase 1, and we compare the model with several well-known spoken language model, and we found that on dynamic super phase 1, DESTA 2.5 can get the best performance. Then we also try the model on a well-known benchmark called MLC-SLM, and the model did not get the best performance on all the categories, but compared with our baseline, it get the best performance on average. And it is reasonable that the model did not get good performance on music because, as you can see in the previous slides, we only have very limited music data. And we also submit to the leaderboard of MLC-SLM, and DESTA 2.5 is only worse than Flamingo, Qwen, and Gemini. Those models are created by big companies. And we only have very limited data for music and environment, so you can consider that our model almost give up this category. If we only consider the speech data, speech category, actually DESTA 2.5 is comparable with other models. And here are more results. We evaluate the model on the benchmark called Sakura. And this benchmark is created by my PhD student, Zhikai, and this is a paper presented in this Interspeech. So the idea of Sakura is to evaluate the reasoning capability of the model. Usually today, when we evaluate spoken language model, we provide a single hop question. For example, you give it a dog barking sound, and you ask, what do you hear? And the model will say, I hear a dog barking. And however, if you make the question be more difficult, you make the question has to be answered with multiple hops, then the model cannot answer the question. If you ask the model how many legs does animal that makes the sound have, even though the model knows the dog has 4 legs, even though the model can recognize that the sound is a dog barking, when you put these two information together, the model cannot answer the question correctly. So this is something interesting about the reasoning capability of the model. You can check the paper for more details. So here's the result of DESTA 2.5 on Sakura. And you can find that although the model do not get the best performance on single hop question, but it get the best performance on multiple hop question. And the other benchmark we try is speech IF eval. So for this benchmark is created by my PhD student Kehan, and is to evaluate the instruction following capability of the model. We found that today's spoken language model are good at some typical questions, probably you have seen in the training data, like what emotion is in the speaker. However, if you add some extra instruction, for example, you ask the model to answer in capital letters, some model just cannot answer the question. Originally, the model can correctly answer the question, what emotion is the speaker expressing? But if you ask the model to answer in capital letters, suddenly it cannot answer this question, and some model just start to do speech recognition. It just ignore the task you asked it to do. So to benchmark the instruction following capability of the model, Kehan create a corpus called speech IF eval. And we evaluate the model by instruction following rate, the higher the better. And DESTA 2.5 get the best performance for instruction following rate. And here we have another measure called delta here. The delta means the instruction following rate difference between the original text model and the speech language model. Because those speech language model are fine-tuned from a text language model, so you can evaluate the text language model and the fine-tuned speech language model. And we found that in most cases, the text language model, the original one, uses the backbone of the spoken language model, achieve much higher instruction following rate. And when you fine-tune the model on speech data, the instruction following rate become lower. So here on this figure, we show the performance on several models, and vertical axis is instruction following rate. Red dots, the red points, represent the instruction following rate of the backbone text language model, and the blue points are the performance of spoken language models. And you can find that after fine-tune the model from a text model to a spoken language model, the performance, the instruction following rate of the model becomes worse. But if we take a look at the performance of DESTA 2 and DESTA 2.5, they are at the rightmost on this figure. Their degree compared with the text model is very minimal. And here we have some ablation study to show you who generate the data, who generate the caption data for training is very critical. Here, our backbone text language model is Llama 3.18 billion. And we use different model to generate the training data. We try to use Llama family to generate the training data, and we also try to use QWin and Gamma to generate the training data. And from the result, here you can find that here we evaluate on 4 benchmark, larger performance, larger values means the better performance. And you can find that if we use llama to generate the training data and train the llama to be a speech language model, we can get better performance compared with the training data generated by Qwen and Gamma. And you can find that here, when we use Qwen to generate the training data, we put not available here, means the performance is so poor, the training data just crash the model. Probably you will think, is it because Qwen do not generate proper training data? This is not the case. If we change our backbone language model, if we use Qwen 2.5 as the backbone language model instead of use Llama 3.1, then the same training data set. Here, the two lines in the black box, they represent using the same training data set, both generated by Qwen 2.5. And if your backbone is also Qwen 2.5, you get much better performance, even better than our original result using Llama 3.1 as the backbone. So this experiment showed us which model generates the training data is very critical to how good your spoken language model can achieve. So this is the first story about fine-tune a text language model to listen. Then in the second part, I'm going to share with you how can we also make a model speak. So we already know we can fine-tune a text language model to be a speech language model. They can take the representation from encoder or token from an encoder as the input. We can, of course, further fine-tune the model to make it output speech tokens. It can output speech tokens auto-regressively, just like a text language model can output text tokens auto-regressively. If you can train a speech language model to output speech tokens auto-regressively, then you can make the model output speech. You need a decoder. The decoder takes the speech token as input and generate the raw waveform. Then your model can respond with the speech waveforms. And I'm not going to go through the details of how to train these speech tokens. If you are interested in this paper, if you are interested in speech language model, you can take a look at this paper. Okay, so here what I'm going to discuss is what is the benefit of starting from a text language model for speech generation. So I think the benefit is if we fine-tune a text language model to be a speech language model that can generate speech token, then the model can not only generate speech token, but at the same time, the model also have the capability to generate text token. This is the original capability that text language model have. If you carefully fine-tune your model, you can keep its original capability so it can still able to generate text token. If the model can generate both speech and text token, then you can do text and speech hybrid generation. So your model can have two language model head, one head for text token and one head for speech token. So at each time step, the model generate one text token, one speech token, one text token, and one speech token, and so on. And your decoder will take the speech tokens as input and generate the speech. If the decoder only takes the speech token as input, why we bother to generate text token? But the literature already, lots of literature already show that this kind of hybrid decoding is very helpful because those text tokens serve as the inner monologue of the speech generation. So your model, before it really says something, it can generate text token as a draft of what the model wants to say. And it's very helpful to make the generation more stable. But the challenge here is the text tokens and the most existing speech token, they have very different scale. Usually, the speech tokens are frame-wise, probably each token corresponding to a fixed period of sound, such as 0.02 seconds. So given an utterance, its corresponding text sequence and corresponding spoken token sequence can have very different length. And usually, the speech token sequence will be much longer than the text token sequence. And their alignment can be very sophisticated. They can have very complex alignment. Each text token corresponding to a different number of speech token, and given the same text token, if its context is different, usually corresponding to different number of speech token. So the alignment between the speech token and the text token can be very sophisticated. Therefore, lots of different sites try to invent different strategy for text-speech hybrid generation. Here I list 3 potential strategies. I'm not going to go through the details. There are many different strategies because the text token and the speech token, they are very different, and it's not trivial to align them. So it's not trivial to do text-speech hybrid generation. And here we are going to think in a different way. So if we consider text-speech hybrid generation as a paradigm, we are going to train our speech language model to speech. Then can we design speech tokens? Can we have speech tokens that design for this kind of hybrid generation? For speech token design for this kind of hybrid generation, I think it has to fulfill the following characteristic. One is it has straightforward relationship with text. We want to have audio token which have straightforward relationship with text. In this case, those tokens cannot be frame-wise. They cannot correspond to a specific period of time. They cannot be corresponding to a short period of time. Let's say the straightforward relationship is we want to have one speech token corresponding to one text token. Then probably we can have the encoder like this, given an utterance. If the utterance have 3 tokens in it, then the encoder also generate 3 corresponding tokens, 3 corresponding speech tokens. Each speech token corresponding to 1 text token. So this is straightforward relationship, although there are other possibilities. If we say 1 speech token corresponding to 1 text token, then the hybrid generation would be so trivial. The model only have to generate 1 text token, then 1 speech token, 1 text token, 1 speech token. You do not have to worry about any issue of the alignment. The second consideration is probably those audio tokens do not have to include the content information. Today, lots of people are working on this kind of speech tokens, and usually when you train the speech token, you want the tokens to include everything. So you want the token not only include content information, but also processing information, speaker information. You want the model to contain everything. However, probably there's no need to include the content information if we know that we are going to do text-speech hybrid generation. So if our decoder can take not only the speech tokens as input, but also the text token as input, then the speech token do not have to focus on, the speech token do not have to contain the content information. It can focus on something beyond text information. It can focus more on speaker or processing information. And the decoder can get the text information from the text token, so the audio token do not have to contain the text information. So to have this consideration in mind, we propose a new speech tokenization technology called TEST. This is mainly done by my PhD student Liang Xuan and cooperate with Wai-Shi Chen from MediaTek. So the basic idea of TEST is like this. So this is the overall framework of this kind of tokenizer. We also start from a pre-trained speech encoder. It's still frame-wise, each frame corresponding to a specific period of time. Then we assume we have the ASR, so we know the transcription of the input output. Then we have an aggregator, is several layers of attention, and we consider, in the attention you need query, key, and value. We consider the text tokens as queries, and the last layer from the speech encoder as the key, and the middle layer as the value. Then we do attention, so this is the attention So we have the query, we have the key, we have the value, so we can do attention. And each token serves as a query, and it gets the information from the values, then you output a token. So each text token will generate one speech token. So if the input is how are you, how corresponding to an audio token, and are corresponding to another, and you corresponding to another. So this is our encoder. It includes a typical speech encoder and an aggregator. Then our decoder will take both the text and the audio tokens as input and synthesize the speech signals. Here our decoder is actually similar to a TTS model because it takes text as input. So it's something similar to TTS model. We directly use the network architecture of cozy voice. But different from typical TTS model, the model not only takes the text information as input, we have one audio token corresponding to each text token. And this audio token will tell the decoder how to pronounce a specific word, how to pronounce a word. Then we train the model end-to-end by minimize the reconstruction error, just as typical way to train the tokenizer. And this is the basic idea of text. And to show you that this audio token encodes some information related to how to pronounce a word, but is not text dependent, we have a simple demo here. So here you will listen to two authors. The first one speaks very slowly.
The captain's face had been buried in a pile of papers. But now Murdoch came around to stare at the gang leader.
Okay, someone speak very slowly. The next sentence.
Any news on the dance at the Salt Cans?
It's very fast. Let's play it again.
Any news on the dance at the Salt Cans?
Okay, so we have two alterns. So the encoder takes the both alterns as input and generate the audio tokens or audio token sequence for the two input alterns. Then we switch some of the tokens in two alterns. So the token corresponding to can around 2 become the audio token of news under, and vice versa. Then we use the decoder to resynthesize the speech, and you can listen what is the difference. So let's listen to the slow alterns. So now it becomes like this.
The captain's face had been buried in a pile of papers. But now Murdoch came around to stare at the gang leader.
So you can follow that 10 around 2 become faster, or you can play it again.
The captain's face had been buried in a pile of papers. But now Murdoch came around to stare at the gang leader.
So you know at least this token includes some clues about speaking rate. So for the faster one, now the news under, the 3 tokens, news under should be slower. So this is the synthesized result.
Any news on the dance at the Salt Cans? Any news on the dance at the Salt Cans?
So you can follow it if you compare with the original alterns, the news under becomes slower. Then we can train our speech language model with the text tokenizer. So we now can transform the speech into tokens. So we use the Emilia as our training data set. We use English subset contain 40,000 hours, and we have the transcription. And for each text token, we can find a corresponding speech token. Then we initialize the model with Llama 3.21 billion base model. We use Llama 3.21 billion base model as our initialization model and train the model. They can generate one text token and one corresponding speech token at each time step. We only train 1 billion model because we have limited computing resources. So welcome anyone, if you have computing resources, to try this technology on a bigger model to see what we will find. Okay, so it's just a pre-trained model. Okay, we trained it on Emilia, a large speech corpus without any instruction fine-tuning. So because it's a pre-trained model, so we compare our test language model with other pre-trained models. When you evaluate the pre-trained model, you usually ask the model to do continuation. You provide different model the same prompt, and different model will continue with different speech signals, and you evaluate how reasonable the continuation is. We evaluate from 3 aspects. One is directly use ASR plus language model to evaluate whether the semantic is coherent, and we use UTMOS to evaluate whether the continuous speech signal is good quality, and we also as human to rating how reasonable the whole authors are. And here is the result. So 3 different colors corresponding to 3 different metrics. Here we compare with other pre-trained models, and you can find that compare with other pre-trained model, our model although is significantly smaller than other model. Usually people use 7 billion parameters today. Even though we have a smaller model, you achieve better performance. And we also compared our model with some instruction following model like Llama Omi. You can check the result in the paper. I want to highlight that it's unfair to compare this pre-trained model with instruction following model, but we found that if you give the model a question, sometimes it still generates the answer. So you can compare with the instruction following models. So besides those numbers, I think it's more interesting to show how the model works, so show the performance of the model with the continuation. So here I tried several examples. So the first one is just a typical one.
I'll take the armchair
So someone take the armchair, then what would happen?
in the corner and just sit there. It'll feel better. I'll try to not sleep.
Okay. Then this is another example,
I reserve your services
and this is the continuation.
for a long time. I am very happy with the result. I will definitely recommend you to my friends.
Okay, so usually the model can generate something reasonable and intelligible. And I try an alternance from the Big Bang Theory. It's hot and loud and there's so many people. This is what Rajesh say, and this is the continuation.
I don't know what to do. I'm not a fan of crowds. I'm not a fan of loud music. I'm not a fan of being in a crowd. I'm not a fan of being in a big city.
Okay, so the next one, this speech prompt is very well known.
Look in my eyes.
And so this is from a Bilibili content creator, and if you know this creator, you know the ground truth is, tell me why, baby, why. And this is what the model continued.
I'm not the one who's wrong. I'm not the one who's wrong. I'm not the one who's wrong. I'm not the one who's wrong.
He just repeat. He's not the one who's wrong 4 times. And after we have this model, I try lots of different random things. For example, I try this one. So in case you do not know what is this, I prepared the ground truth and I want to play it in my talk. So it's like this. So now you know what the ground truth is. So here, if the prompt is Ruby High, and you know the ground truth is Nagigasubi. This is the only Japanese sentence I know today. So, but the model is only trained on English, so it cannot output Japanese. So let's see what's the output of the model. So this is the prompt, then it's continuation.
I'm Ruby, a third-year PhD student in the Department of Computer Science at the University of Cambridge. I'm currently working on a project to build a language for describing and reasoning about security policies.
I also try other examples. So this is Ayumi-chan. And this is a continuation.
I'm a new member of the club. I'm from Japan. I'm studying in Australia. I'm a big fan of anime.
And so the last one is not as successful, is Shiki-chan.
I'm the host of the podcast, Girls Guide to Travel. I'm a travel writer, photographer, an educator. I've been traveling the world for over a decade, and I'm passionate about sharing my experiences with you. Passionate about sharing my experiences with you.
Yeah, I know the content of the author is a little bit weird, but this is what we can get with our tokens. And for the last part of this talk, I will going to show you how to add reasoning to a speech-to-speech model. Everyone knows that today text language model can be improved with the reasoning process. So besides directly generating output, the language model can generate some reasoning tokens. They are basically the text token and not shown to the users. And for speech language model, of course, we can consider the similar direction. So besides directly output the speech response, the model can generate the reasoning token. There are also text token. Then the model generates the text token, reasoning token. Then it generates the text output. By the way, here from this slide, I will not going to show the hybrid decoding to simplify the slides, but keep in mind that in most cases for this kind of speech generation, we now use hybrid decoding. We use the text and speech hybrid decoding. And previous literature have shown that adding reasoning is also helpful for a speech language model. But the drawback of adding reasoning to the speech language model is the model cannot respond immediately. It generates the reasoning tokens first, so the user have to wait until the model finish the reasoning, then the model start to talk. Human usually have to wait for a while the model is doing the reasoning. So we'll consider, can the model generate the speech output but also do reasoning behind the scene at the same time? Can model generate two sequences simultaneously so the model can benefit from reasoning but do not have the delay from the reasoning? Originally, I think probably we need a new network architecture, probably two decoders with the cross attention. But now we found that it is unnecessary to do that. You can use the language model architecture, just the typical language model to achieve simultaneous thinking and talking. We call this idea Stitch, and it's invented by my PhD student Chen Han and a group of Microsoft researchers. So this is the idea. Here I'm going to use GLM for voice spoken like speech language model as an example to demonstrate the motivation of Stitch. So in GLM for voice, in each time it generates 39 tokens. Actually, it's hybrid of text and audio token. It generates 13 text tokens and 26 audio tokens. Okay, so it generates 39 tokens. And these tokens will be the input of the decoder and become the waveform. While the waveform is played, at the same time, the language model have to generate another 39 tokens. And before the audio clip is being played, is being completed, it is finished, we have to transform the tokens into the waveform by decoder. If the language model can generate the 39 tokens fast enough, then you will consider the audio clips do not have discontinuation. Is the model powerful to generate 39 tokens while playing the speech? Usually it is. For 39 audio tokens, it corresponding to 2 seconds of waveform. And to generate 39 tokens, if you have A100, it only takes about 0.5 seconds. So actually, there is a 1.5 second buffer there. Your language model do not have to do anything. How about we just use this buffer to generate the tokens for reasoning? 1.5 second buffer is already sufficient to generate 100 reasoning tokens. So this is the basic idea of Stitch. So typical way to do the reasoning is like this: speech input, reasoning token, and speech output. In Stitch, what we do is like this: speech input and reasoning a chunk. So each chunk is 100 tokens. The model generates 100 tokens for reasoning, then it starts to generate speech tokens. And the speech token transforms into speech signals, and at the same time, while the speech signal is playing, the model continues to generate reasoning token and generate speech token. Before the end of the audio playing, if we can generate a speech token, then the whole audio signal will be continued. People will not consider there is a discontinuation between the two audio segments. And we have tried another idea. The model says something before reasoning. So when there's a speech input, the model starts to generate a segment of audio token, and while audio token transforms into speech signal, while the speech signal is playing, the model generates reasoning token and more audio token. Before the end of playing, the model can synthesize the speech, and for the listener, for the user, they will not notice the discontinuation. We call the first idea reasoning first, and the second idea speaking first. So this is the basic idea. Then the question is how to prepare the training data. So we prepare the training data in this way. There are already lots of speech-to-speech dialogue data set, like Voice Assistant 400K. You can check more detail about the training data we use in our paper. So we already have speech input and speech output, and we can generate a transcription by ASR model. Then we use the text language model to generate the text reasoning between the input and output. We just tell the model, given the input, given the output, what is the proper reasoning process, and usually today text language model can give you the reasoning process. Then after we have the reasoning process, we split the reasoning process into the chunk one by one. Each chunk have 100 tokens, and we also have to split the speech output. And for speaking first scenario, you just ask the model to generate the first speech chunk and generate the first reasoning chunk, the second speech chunk, the second reasoning chunk, and so on. This is the learning target of the model. And we start the training from GLM4 voice. And here is the experimental result. So you can check more detail about the training data set we use in the paper and how we evaluate the model. Here I just show the accuracy among all the tests we have evaluated. So our first baseline is GLM4 voice. We achieved 53% accuracy on the testing set. But before we try reasoning, we do fine-tune GLM4 with our training data, but without reasoning. This is necessary because probably GLM4 have never seen our training data, and our training data is new to GLM4, so it can improve the performance of GLM4. So if we see the improvement, it's not necessary from the reasoning. So if we train GLM4 with our data and with our reasoning, we did see some improved from 53 to 62. However, if we evolve the reasoning process, here we first try typical reasoning, then the performance improved from 62 to 79. What the most important part is, with the speech, with the idea of speech, we only have very limited minimum performance degradation. So even we do speaking first, the model speaks something, then do a reasoning chunk, the performance only degrade from 79 to 78. And I have to highlight that for speaking first, its latency is just the same like the result without any reasoning. So for speaking first, there is no latency latency from the reasoning process. So with the reasoning process, with the idea of speech, we can improve from 62 to 78% accuracy without any latency. And I also want to mention that the audio quality is not influenced. We have more results in the paper. And we have tried other idea. One idea is dynamic reasoning chunk size. I mentioned that for A100, you can generate 39 tokens in 0.5 seconds. But what if we do not have the GPU as good as A100? If your GPU is worse during the inference time, then generate 39 tokens can be longer, then your buffer will be shorter, so you can only generate less reasoning tokens. So the reasoning token, how many reasoning tokens you can have in a chunk is device dependent. So we want to know that if during the inference time, if we change the size of the reasoning chunk, what would happen? So during the training time, the reasoning chunk always have 100 tokens. But during the testing time, during the inference time, we try different reasoning chunks to see how much performance it would degrade. So this is the performance. So each line corresponding to different corpus. The vertical axis is the accuracy, the larger the better. The horizontal axis is the number of tokens in each reasoning chunk during the inference time. First, you can find that it is obvious that if you have shorter reasoning chunk, then you have worse performance because it's mismatched with what the model have learned during the training time. However, compare the result without any reasoning. So here the dot represent the result without any reasoning. Reasoning with shorter period of time, reasoning with shorter reasoning chunk still improve the performance in many cases. Then we also consider what would happen if the reasoning process is not generated by the speech language model itself. Instead, you use another more powerful text language model to generate the reasoning process. So you can use the text language model to generate the speech, but use the text language model to generate the reasoning process behind the scene. So the two models can cooperate with each other. So this is what we did. So for speech language model, it takes an utterance as input. For text language model, we have ASR to transcribe the utterance, so it has the text input. Then for speech language model, it generates some audio tokens. And because here we actually use hybrid decoding, so the speech language model not only generate audio token, but also text token. So text language model can actually read the output of the speech language model. So text language model take the output of speech language model as input, and it generates the reasoning process. It generates a reasoning chunk. And the speech language model take the reasoning chunk from the text language model, although it's not from the speech language model, it's from other language model, but probably it's more accurate, more powerful. So speech language model take the reasoning process generated by another model as the input and generate more speech tokens and so on. Then let's take a look at the performance. So here, the red line is the original result. So the red line, we use the speech language model itself to generate the reasoning process. If we use the better model, here the purple line is the result. Use GLM4 9 billion chat as the model to generate the reasoning process. If you have a more powerful text model to generate a reasoning process, then you can improve the performance of the whole process. You can improve the performance of a speech language model and text language model as a whole. And if you use the worst text language model, here we use Llama 1 billion, and it's much worse than other model, then the overall performance will be degraded. And this is an evidence to show that this speech language model, they really rely on the reasoning process to get the correct answer. They did really look at the reasoning process to generate their result. So if you provide better reasoning process, the performance is better. Worse reasoning process, the performance is worse. So for the last part here, I showed you a demo how the model looks like. So this is the result.
Claire makes a 3-egg omelet every morning for breakfast.
This is question.
How many dozens of eggs will she eat in 4 weeks?
Claire makes a 3-egg omelet every morning, and there are 28 days in 4 weeks. That's 84 eggs in total. Since there are 12 eggs in a dozen, she'll eat 7 dozens of eggs in 4 weeks.
Okay.
The answer is 7 dozens.
I know the characters here is small, so let me describe it a little bit. For the green token, they are reasoning token. They are the token generated behind the scene, so the model do not really read those green tokens. And for the yellow token and the red token, yellow token are text token, red tokens are audio token. The model generates the yellow token and red token in a hybrid mode. We find it from GLM4, is a hybrid generation model. So the model will read the text token in the yellow part and finally generate the red tokens. And you can find that during the whole process, after the user asks a question, there's no delay. The model directly generates the audio token without any delay, without delay from the reasoning. So this is all I want to share with you today. And last but not least, if you want to learn more about spoken language model, here we have a review paper. This is mainly led by Karen, and Shinji is also the co-author. If you want to learn more about spoken language model, you can read this overview paper. So this is all I want to share with you today. Thank you very much. Thank you.